hash. And that's what I attach to the hash. So for instance, for the first object, I get this bit sequence of 0, 1, 0, 0, 1, 1, 0, 0. And a very natural thing to do in this case is to give it a value of 0. There's no 1. Let's say the star comes along and the last 2 bits are set to 1, and then there's a 0. Okay, it gets the value 2. And then something that's a bit less frequent, namely, it occurs with, 2 to the minus 5 probability. Okay, so actually you can see that there's something wrong with the hash that I'm assigning here. I would basically need to add a 1 to it, because obviously this first line cannot be true, right? Because if this occurs with probability 2 to the minus 0, it means it occurs with probability 1, so this is wrong, right? Anyway, so this would be actually mapped into a 5. Okay, fine. So now essentially what I'm looking for is the position of the rightmost 0. That's really, so you can see this table is wrong by 1. Now, basically, it's quite easy to see that the probability of the rightmost 0 is, is 2 to the minus j. Because, this one didn't work, this one didn't work, this one didn't work, this one didn't work, and this one worked, right? And I don't care about the rest. And you can immediately also see that, sum over j, 2 to the minus j, sums up to 1. So it's properly normalized, so that's also a useful sanity check. And so now I'm interested in the maximum of this quantity. We know that this is the cumulative distribution function, 1 minus that. So 1 minus that raised to the power n is exactly, the CDF for the distribution of the maximum, which is kind of nice. So we have a fully and very compact analytic expression. It's still not that nice to deal with. What I'm actually interested in is, how far will this typically deviate from its expected value? So intuitively, you would think that, if I have n distinct objects, then, the number, that position will be somewhere in the order of log n, log base 2 of n, right? And now the question is, how much can it deviate either way from log base 2 of n? And I'm going to use this later on. You can basically then use this maybe by invoking more than one of those sketches to design an estimator of those counts. Now, it sounds awfully contrived, rather than, struggling with log n bits, I want to get something that is represented in log n bits. But if you think about it, if you have very large counts and a lot of those counters, then, squeezing out that extra factor of 10 or 20 can actually make a difference. So especially if you have very large counts. Okay, so what I want to prove now is that the probability that the max over those hashes deviates from log number of those counts by more than log c is bounded by 2 over c. So this is similar to essentially, a Gauss-Markov type of inequality where we also have that range, except that, now we have the logs throughout, but that's just a way of writing it out in a slightly more cute way. And I'm going to go with you through the very simple proof of basically of perfect hash functions. If you want to go through the proof with two-way independent hash functions, which is a lot more complex to write out, then you would have to see this paper by Alon, Matthias, and Szegedi. And, they got a prize for that paper for a good reason. Okay, so let's look at that. So we already know that, for any number to be, at the position j, it's going to occur with probability 2 to the j. So if I want to make sure that I don't have anything of j and larger, I get this, right? So now, of course, if I invoke this entire thing x times, so that's my domain, that's a probability that none of them will exceed. And I want to make sure that this is less equal than 1 over c. Right? That's what we want to bound. Because if we rewrite this, this is of course nothing else than log x minus j less equal than minus log c. So this, okay, yeah, ignore the hello world, but this is basically one side of the bound that we need to show. But, you know, that holds trivially because I just set this up this way. So basically this is trivially equivalent to that expression, so the upper bound holds by definition. Okay. For the lower bound, we have to do a little bit more work. So the probability of not exceeding that threshold is bounded by 1 minus 2 to the minus j. And now, since I need to make sure that none of them exceeds it, I have to bound it by x. Well, basically I have to raise it to the power of x because I'm invoking it, you know, x times. And, well, then I just use the fact that, you know, 1 minus a is less equal than e to the minus a. So this is therefore less equal than e to the minus, so see there's a typo here, 2 to the minus j. And now, since this is an exponent, so it comes in as a product, so we have size of the domain. And, well, I want to make sure that this is less equal than e to the minus c. But that holds just by construction because we put that exactly into our requirement. So and of course this is then less equal than 1 over c. So what this gives us is both an upper and a lower bound on the value that this Flajolet-Martin counter will achieve. So basically, you know, if here's log x, then we know that with probability at most, you know, 1 over c on either side, it's not going to deviate from the estimate by more than log c, log base 2 of c. Okay. Sorry, forget the log base 2, just log c. Okay. So this is kind of a useful thing to have. Now, if you say, well, that's not good enough for me, well, then you could, for instance, go and take more than one of those sketches and take their median, or you could take the average, and then you argue accordingly. And this allows you to boost the probability just in the same way as what we did last week. So does anybody have an idea of what I could do if I don't like this quantization? Because, you know, getting things wrong by 50% is quite bad, right? So how can I do better than, you know, getting things wrong with 50% accuracy? Pardon? So you could basically make the condition for 2 bits at a time. This way it will get more coarse. then you wouldn't have, you know, accuracy of 50%. You'd have an accuracy of only 25%. But you're exactly in the right direction. So basically, the direction of, you know, making it even more aggressive is easy. That's doing exactly what we suggested. So how do we squeeze more bits out of it? Basically, how can I get half bits, right? You could possibly do that, and then you essentially doctor with a probability of seeing something. Yes, you could do, yeah, that actually would work. You'd basically take a pair of bits, so similar to this, and you, for instance, you know, accept if you have not just a 0, but 0, basically, you only reject with, you know, when you see a 1, 1. And this way you can go from 50% to 75% accuracy. That's a very nice idea. And this doesn't require any extra memory. Or you can actually just have a probabilistic incrementer, where you essentially generate a random number, and, well, a hashed random number, obviously, and then you increment your counter whenever you see this thing. But actually adding more bits is much cleaner. So what you suggested is much better. Okay, so basically, overall, the idea is, if I have a single bit, then 0 or 1 occur with 50% probability. Now, if I have, for instance, you know, 0, 0, 0, 1, 1, 0, 1, 1, I could just accept only with this, and then I accept only with a quarter. Or I could accept all of these terms here, and I'd accept with, well, 3/4. And so this way, I can actually trade off the accuracy, and as long as I'm okay with getting things right within a suitable quantization of powers of 2, then this is pretty good. So obviously, if I do this, I have to pay more bits. So there's a limit to how far you would go, but this would pretty much do the trick, and you could then show that for these terms, the same inequality holds. Okay. So this is actually nicer than what I had here, because there are some versions of the Flajolet-Martin counter which don't store the log of the sequence, but actually, you know, start storing parts of the sequence itself. Forget that. What we had before on the here on the notes is actually much cleaner. Okay, good. Any questions about that so far? Okay, it was fun now. Okay, so this gives us a good estimate of F0. If I, you know, want to be able to be particularly space efficient, I would go and, you know, invoke something like this several times, so you get high accuracy, and yeah, so it's quite effective. Now the next thing that you care about possibly is F2. And so this is basically again from this paper by Alon, Matthias, and Szegedi, and I'm probably butchering that because they're all Hungarian names. Actually not the first name. The first author, he's, I think, Israeli. Noga Alon. Anyway, the strategy is very similar to what we already had before, where we used this average median theorem, right? Where we basically take micro averages and then we take the median. So the idea is to design a random variable whose expected value is F2, and then show that, you know, it has not too horrible variance, and, you know, take many of those averages to get that number. So the random variable in question in this case is a sum over sigma of x, I, and j, where sigma of x, I, and j is a Rademacher hash. In other words, it has with equal probability 1 or -1. And for the sake of this analysis here, I'm just assuming that it's a perfect hash function. So, yeah, so first of all, yes, there's the theorem and it's directly applied, but what's actually a bit more fun is the proof then. So we have the theorem, we have that proof, but now let's actually look at what happens with F2, because we've already done all the hard work last week. So for the mean, this is fairly straightforward, right? Because what we can immediately see is for the squared quantity, the only terms that survive are where sigma of xi and j occurs twice in expectation over the hash functions. Because whenever cross terms occur, since we know that the expectations are 0, and since we assume the ideal hash functions, you can see that this actually vanishes. So that's that. As a matter of fact, the only property that we would need to get the mean right is a pairwise independent hash function. Because by linearity of the expectations, that's all we need. Furthermore, to get the bound on the variance, all we need is a four-ways independent hash function, and that will also probably do the trick, but that's a different story. Okay. So given that we have this, we now need to get our hands on the variance. And, well, the first thing to notice is that out of all those terms where we now need to raise that sum to the power of 4, the only terms that survive are where the xi's are basically, you know, the x's occur either twice or 4 times, or not at all. Because if they occur an odd number of times, the expectation will vanish. So that's, I mean, that's kind of straightforward. Now what you need to do, and we can go through this in detail, or you can just, you know, believe it, and it's not terribly deep and not terribly inspiring, but basically you just need to look at all the cases where, you know, you can have pairs, where you can't have pairs. You just need to count. And so what you see is, and that's basically where those factors 3 and 2 come from. After doing the right counting, you'll see that it's basically the sum over nx squared nx prime squared minus 2 times the sum over nx to the 4th. And that's just because if you square this, you are overcounting, and by just, you know, being careful about the relative counts, you get the factors of 3 and 2. Does somebody want to see the details? Okay, nobody does. Okay, good. Now all we have to do, and by the way, here's another typo because this should be exponentiated, obviously, raised to the power 2. To get the variance, it's the expectation of x squared minus the expectation of x squared. Okay? And so then we just get, you know, 3 times. So this is basically f2 squared, actually. And this is f4. But we are subtracting it. So we have 3 times f2 squared. Well, if we subtract it, it's basically 2f2 squared minus something else. So this is, of course, bounded from above by 2f2 squared. So it's kind of nice because we now have a random variable where the variance is twice the expectation squared, right? So you could probably actually tighten some of those guarantees up a little bit. And then if you plug that in and do the reasoning about the encoding and so on, you'll see that you need that many bits to store, well, to estimate f2. You need that many bits because what basically happens is you need a number of estimators for this quantity here, for f2 squared. And so these are the various xij's that you compute. And then in the end, you average and you take the median. And yeah, go ahead.
I'm not sure what xij is. X is in the stream, so what do ij represent?
Okay, so little x. Okay, so little x is in the stream. I and j are just additional parameters that you throw into the hash function. So this way, you can basically generate different hash functions. Another way of writing this would be sigma subscript ij of x. So the way how you implement this in practice is you take something like murmur hash, right? So by the way, never implement your own hash function. And if you need something that's fast and not cryptographically safe, so basically, MD5 or whatever is the latest flavor, use this thing called murmur hash. And go to Google Code and look for SM hasher or smasher or whatever. So that has the latest version of this. It's very, very fast, as in it takes, has a throughput between 5 and 10 gigabytes per second, which means it's actually not too far away from main memory bandwidth. So that's what you should be using rather than writing your own. It's not cryptographically safe, but it's safe enough for machine learning, because you really don't need strong cryptography for that. Now what you would basically do is you would invoke hash of whatever payload, and then you would basically concatenate this, and you'd have basically, I, and then you'd have j. So if these were strings and this is C++, then the addition operator is overloaded anyway into string concatenation, and you just hash that all up. Does it make any difference whether I put the I and j as a prefix or as a postfix? Is there any difference? Who thinks there's no difference? Okay. Who thinks that there is a difference? Okay. It's a numerical difference, yes, but in terms of how the algorithm works, is there any difference? No, exactly, because both of them will, if we have a perfect hash function, will map even slightly different inputs into something entirely different anyway, so we won't have to care. Be careful if you do this in Python. Python will actually, if you feed an argument into its hash, will try to come up with another hash value that's not too far away. There are some cases when this is useful, but this one clearly isn't. So be careful if you use Python.
Like the default?
Yes, the default hash in Python on strings. Try it out. Quite often, subsequent values will be very close. This is a known feature. I will call it a known bug, but yeah. They specifically picked one of those hashes. So if you...
So this is what I use in the dictionary in Python?
I don't know. If the Python dictionary is implemented in Python, which I don't think, they would be using it. They might still be using it because the guy who implemented the dictionary didn't really understand what he was doing. That said, for a dictionary, this may actually not be such a bad thing, because if you just append a little bit to it, you might actually want to be able to use as your default search location something that's close to where you were just before. So in those cases, it is sometimes actually useful to have that kind of a hash, but I find it a little bit troubling that you would do that in general. Yeah, and maybe they fixed it in Python 3, but in Python 2 point something, last time I checked it was. So just be careful. Yeah, so this is how you get a nice sketch. So if you just look at the overall numbers, well, that's just, what we get from averaging. This is our standard Chernoff bound, or basically variance reduction part. We pay that much to reduce our uncertainty. And these are the number of bits that I actually need to store things, because, well, that's how many items I might worst case see. Basically, I need to be able to bound the size of the counter. Yep. Pardon? It's inside the log, yes. because you're counting.
So if you append, right, you are looking at the LSPs, right? So won't that matter?
Well, if you have a poorly implemented hash, it might, but on a good hash, it shouldn't. Because appending to a string should give you a new hash value that is unrelated to what you had before. You could, for instance, implement that by computing some hash of each key and then XORing everything. That would, I mean, this would be a terrible hash, but that, for instance, would make it safe for that very regard. And yeah, of course, you don't go and compute a full hash to just extract one bit and throw the other 31 bits away. So you want to recycle the other ones, but only once. If you recycle the bits more than once, then you will get bogus results. So yeah. Okay, maybe we should have a programming exercise about hash functions at some point. Because a lot of people look a bit surprised. Okay. Now, how do we get fk in general? And it just turns out that f2 is sort of the boundary at which you can do things efficiently, and if you go beyond f2, things get really problematic. But I want to show you this because it's a very simple hash. It's a very simple and ingenious way of designing such random variables. Okay. So the issue is, well, you know, we have the stream, and it keeps on arriving, and we don't really know how long that stream is, and at any time I might be told, okay, stop here, Alex, give me, you know, the best count that you have. And so this way, I mean, you would need to be able to, you know, figure out when you actually start counting. So the idea is, first, you would actually go and, okay, let's for the moment pretend that I know the full length of the sequence, right? So then I can determine beforehand when to actually, you know, at which elements to start counting. So for instance, I decide I will count, you know, we'll look at positions 4, which corresponds to the A, and at position, well, wherever that C is, right? So let's for the moment pretend that I do this. So then I've decided, okay, well, I want to get something that, you know, occurs here. Then I see, okay, it's an A, and then I decide from here on I will just continue counting how many A's I see. And so at the end of the day, I get a 3. Done. And there, well, there is no C that occurs to the right of it. We don't know whether anyone would have happened to the left, but that's it. And so I just then return those numbers 3 and 1. And here's the estimator. I use these counts, so Rij. I raise them to the power k and subtract from it Rij minus 1 to the k and multiply it by the length of the sequence. And then again, I apply this average median theorem as before. So this, when I first saw that, I thought, well, this cannot possibly give me anything reasonable. And I'll show you in the next slide that it does. But let's first actually briefly discuss how on earth you can randomly draw from a stream whose length I don't even know. Any suggestions? Fun? So reservoir sampling, for instance, would do. So essentially what you do is you have a reservoir of positions that you've picked so far, and let's assume they occur with uniform probability. And then when a new element comes in, I randomly evict one of the ones that I currently have with a suitably chosen probability and pick the new one. And so now all we have to do is we just have to work out what that probability is, right? So let's say I'm here at position n, and I've picked, what? Oh yeah, that would help. a lot. And let's just do that with a single element, otherwise the generalization isn't that hard. But okay, so I've picked one of the ones up to here with probability 1 over n. So now this new element comes in, and if I wanted to get a uniform distribution over those n plus 1 elements, right, then what I would need to make sure is that this new element gets picked with probability 1 over n plus 1. Okay, so what I do is (1 over n plus 1) pick the new one. Okay, and throw the old one away. Okay, so what happens? Well, before that, all these terms were picked with probability 1 over n. So basically, P of I was 1 over n. Now with probability 1 over n minus 1, I'm going to pick this new guy. So I'm basically going to shrink this. So this is now happening with probability n over n plus 1, that this will still remain picked. And the new one, P of n plus 1, is just 1 over n plus 1. But this, of course, just works out to 1 over n plus 1, so we're all safe. So this is a very simple algorithm how I can pick random elements. Uniformly random, yes. Very good point. Now, if I had something else than uniformly random, well, for arbitrary distributions, of course, it's kind of hard to do this, but you can start thinking about for which distributions you can still get away with it. And effectively, what you need to do is you need to exploit this multiplicative property. Right? And so basically, for any distribution over n elements for which this multiplicative property holds, well, you can do it. So you could, for instance, pick each new element with probability 1/2. Then you would get a distribution of elements where the last one is picked with probability 1/2, the next one with 1/4, and then 1/8, and so on and so on and so on. Right? So this is what happens if you pick a constant. You will get an exponential decay. So depending on how aggressively you pick the new guy, you will actually get different, expected lengths and durations for past samples, which is kind of useful. Okay.
So do we get anything useful, like any useful distribution family, like exponential or something like that?
That's a very good question. And, well, I'm fairly sure somebody actually thought about this. I don't know, and that's just because of my ignorance rather than because of this being an open problem. But yes, there's probably some very nice properties that you can get there. Okay. Anyway, so now let's look at what happens in terms of this, fk, because we need to figure out that we're actually computing the right thing. And here's where the nk to the k, sorry, ni to the k minus ni minus 1 to the k comes in, because now things telescope. Because with probability appropriate to that, we are getting sums 1 over k plus 2 to the k minus 1 over k and so on. And we get that for each different element in that dictionary. And now this is, of course, exactly fk. So we're safe. The downside of this approach, and you would have already guessed that by just looking at it, is these terms can be huge, and the variance is actually quite monstrous. So if you look at it, the variance is basically, it goes like fk squared, and then times size of the alphabet. So it's ugly. And the problem of that is basically that, well, we don't really win because we need essentially as many bits as the support of the domain to estimate fk. And the really surprising result is that, well, the rate is tight. So in other words, we don't have any chance of really doing much better than brute force for large k. How do you prove this? That's a good question. So there's about maybe 4 pages in the AMS paper, and that's the biggest contribution actually to show that this rate is tight. And you basically construct a sequence which doesn't. So by all means, have a look at this paper. It's a fairly substantial piece of work. It's probably about 30, 40 pages long. Have a look at that. By the way, just getting back to this, another way of performing this uniform sampling is simply you compute the hash of the counter. And whenever the hash of the counter is less than the current counter, you pick the new guy. So this way, you don't need to invoke a random number generator, but computationally, it's effectively the same thing. So this is basically what we already talked about last week. Yeah, actually, probably 2-3 weeks ago. Namely, when you subsample from a stream, you basically, if the hash of the element is the same as what we have, then we increment the counter. Otherwise, we just pick a new element and reset. So as you can immediately see, well, this hash function assigns a random value. The probability that x has the smallest hash is just 1 over the size of the domain. And that's just ignoring collisions. And so once we find it, we just count all the occurrences. So that's very easy. And you can use this to both find all the occurrences for a particular key or use it as a subroutine in the AMS sketch that I mentioned before, where you first use the hash to decide from which position to start on to start counting, and then just count the occurrences. So both of those are OK. But they are slightly different algorithms. In one case, you hash on the counter. In the other case, you hash on the key. Okay. Is everybody kind of cool with that? Because everybody is very quiet. Any questions so far? Yep.
Can you explain a little more what do you mean hash on?
OK. So let's look at the following algorithms. And that might explain it. So while x arrives, OK. Actually, I need to initialize it. I need to initialize I equals 0. So now, when we basically set temp to be infinity. And so I can do the following thing. If hash of x, and I also set c equals 0. OK. This is the initialization. If hash of x is less than temp, then set c equals 1, and furthermore set temp equals hash of x. Else, if hash of x equals temp, then basically increment the counter. And that's it. OK. So that's one algorithm. This algorithm will give you for a random key, namely for the key with the value hash of x equals temp, it'll give you the count. Okay. So, well, okay, so here's the alternative. I increment the counter, so I have I plus plus. If hash of I less than temp, that basically means we are going to start counting again, then C equals 1. And furthermore, temp equals hash of I. Else, if, and I also need to store x, basically x nod equals x. If x nod equals x, then increment the counter. Okay. So those are the two algorithms. I mean, they are clearly very similar, right? The first one triggers whenever a different item arrives, right? Because, you know, for each new distinct item, I get to compute a new hash value. And so only when there's really a new item do I get the chance of deciding, okay, I'm going to pick this one. And so basically when the hash is less than what I already had, then, you know, start again from scratch. Else, if my hash matches, then, you know, just increment the counter. Here, I get to trigger at any given time, because I'm performing the hash on the iterations counter of the observations. And then I do the same thing as before. So it's really just the triggering, and so you can see that by very minor modification of the same algorithm, you can get very different statistics, which is kind of cool.
Which does what?
Okay. So this one will start counting at a random position and start counting that particular object from that random position on. So it might, for instance, find dog at position 530, and then until the end of the document, you know, count the occurrences of dogs. Unless I decide that actually I would much rather start at position 999 and start counting from there on. This one here will pick a random element from the domain of all the objects that I see. It might, for instance, pick dog and give me the total count of dogs, unless I decide that I'd rather be counting cats. Okay, so that's the big difference between those two between those two subroutines.
But the statistic that you calculate is what?
Well, this one's an exact count. This is a random variable. This one is useful for the AMS sketch to get FK. With this, I can do some other things. This is basically, for instance, you know, trying to infer, basically to uniformly draw from the domain and get an idea of, you know, some of the magnitudes that I have. Let's say, for instance, you want to survey an ecosystem, right? And your task is to bring back all, you know, individuals from that ecosystem. But you obviously can't really do that. All the ecosystem, all the, you know, all the specimens that you catch. So you might effectively at random choose to pick one specific variety of fish and bring all of those back. Okay. So the reason why I went into a little bit of detail here is simply to show you basic design templates that you can then use on data streams to design other algorithms that use similar things. So think of this as a blueprint for a hammer rather than a particular beautiful hammer in its own right. Okay. Yep.
Isn't that always going to trigger at the first element?
Yes, that's true. And
Why is it doing that?
well, okay, so it'll trigger at the first element, and if I give you only a single element, then I want the algorithm to return back, I've seen that first element once. Okay. Now, the point is I want to have an algorithm that is correct at any time. So at any time I interrupt it, it needs to give me the correct answer for that question. Now what happens is, for instance, here, with 50% probability, the hash of the second of 2 is going to be less than the hash of 1. So with probability 1/2, I'll throw out the first element and start counting from the second one. Here, with probability 1/2, the second specimen, so the second distinct X, will, evict the first one. So the trick is really, you always have a best bet of what's currently good, but if something else comes along that you'd rather be counting, you throw away what you currently have and go to the next one. And so the probability of you ever switching will go to 0. So for a very long stream, you're unlikely to change things a lot. Yep?
Can you say what would happen if you did the naive thing, which is reject with probability 99.9% or whatever?
Mm-hmm. Okay, good. So, okay, let's check what happens here. This is a bit easier to show for the counter. So I start off with the first element being accepted with probability 1. Okay, that's at iteration number 1. At iteration number 2, the first element will still stay in there with 0.99, and with 0.01, the second element will have been picked. Right? Now, at time 3, this will have been picked with 0.99 squared. This would remain in there with 0.01 times 0.99. And this would have been picked with probability 0.01. So basically, element I would have been picked with 1 minus p times p to the I minus 1. This would be an example of what we discussed before, namely non-uniformly sampling from that stream. So if that's what you want, you should do it. And by playing with p, you can very easily adjust how many items you pick and how long your history is. Because at some point, that first element will become negligibly small, and then everything's safe.
I was thinking of something similar, which is you just keep 1% of everything you see.
Okay.
Like the double thing.
Right. Okay. So if I keep 1% of everything I see, then you need to know beforehand what everything is.
Something I keep with probability.
Okay, so I just write 1% of the data stream to disk. So basically it's like I'm Twitter and I do data analysis Twitter style.
Exactly.
Okay,
So
good.
it goes wrong.
Your disk fills up, then you buy a new disk. Okay, good, fine. The disks fill up, you buy a new computer, your computers fill up, you go IPO. Okay. Okay, I'm not being very kind here, and I'm sorry, this is being teletyped, so nobody at Twitter will ever talk to me again. So apologies to Twitter. They're obviously doing smarter things. Okay, right. So, well, if you did this, then you haven't really solved the problem, because all you've done is you've just driven up the variance, right? And then, you have that 1% sitting on your disk, you have those several disks, and you still need to process it. So while you've made it less painful now to process that 1% of the data stream, the problem remains unchanged. It's just 100 times smaller. In some cases, that 100 times smaller may be good enough that it fits into memory. This is what people do if they can't scale their algorithms for a KDD, right? They just subsample the data set and then say, well, hey, we ran the algorithm on that. Okay, so, but it doesn't solve the problem. You've just made it smaller. Okay, so, but, you know, if you have no idea what you're going to ask about the data later on, this is very well the right thing to do. So if you have absolutely no idea which properties you care about, then it's very hard to design a sufficient statistic of the data. Does everybody know what a sufficient statistic is? Who's seen one before? Okay, good. So given that a few hands didn't go up, it's basically, think of it as a lossless compression of the data. Lossless insofar as if I have any other random variable. Okay, so let's say I have x, and I have any other random variable y. That I can write p of y, given the statistic of the data, and x to be equal to p of y, given s of x. Okay. In other words, s of x captures everything that there is to know about x with regard to any other random variable y. This is one of the reasons why deep belief networks do a really good job on images. Because basically, if you have some representation of your images that lets you reconstruct the image really, really well, right? Then you effectively have a statistic of your image. And then you arguably can do with those parameters as well as you could do with the original image. So by basically trying to squeeze out all the unimportant things and come up with a representation of the data that is more compact. So this is why a lot of deep belief networks have a narrowing down architecture as you go up. You hope to get some results that are, you know, that are basically lower dimensional, and so therefore you need less data to actually do well. There are a couple of other tricks that you can use, but this is one of the reasons why those autoencoders really work. Okay. Good. Yeah. Sure.
But then why doesn't compress sense?
Why doesn't compress?
As famous as deep belief network, for example, right?
Okay. So there's actually a prize-winning paper about 2-3 years ago at NIPS. So this was by, I recall at least 2 of the authors. Would be Daniel Xu, yep, and Sham Kakade. And it may have been John Langford as well. And this would have been around NIPS 11 or 12. I think 12, but I'm not entirely sure. It's, I think, the best student paper or something like that at the time. And here's what they did. So there's this thing called a reduction. And a reduction in machine learning is basically just like a reduction in general in computer science, where you turn a complicated problem into a simpler problem. Complicated problems in machine learning, for instance, are, you know, high-dimensional multi-class classification problem. Let's say you have all of Wikipedia and you have, you know, 10 to 100,000 different categories. So you're screwed. And a simple problem is binary classification. So one of the things that people have been aiming for is to design algorithms to solve the classification problem for high-dimensional problems by converting them into bite-sized pieces that a simple binary classifier can solve, and then do something interesting with it. And there were a lot of explicit constructions of how you can do this, and they designed those tournaments and so on. And that paper actually did a very clean, randomized design to sidestep all those explicit constructions. So if you think about it in hindsight, essentially all the previous reductions were explicitly designed codes such that you had certain incoherence properties more or less with guarantees. And this just designed a randomized algorithm for it. Okay. So the idea is that if I have some really complicated label y and some label set, so let's say, for instance, I have a tree. Okay, let's grow a tree here. Whatever, it doesn't have to be regular, it's just anything, right? So I can encode this as a sparse vector. So for instance, if I'm in the category of, well, maybe Japanese anime, Hello Kitty, God knows whatever, so something very specific and abstruse, I can encode this very specific item, maybe this is Hello Kitty, by a set of bits that I set on that tree in the ontology. Okay. Now this is a sparse vector, and it has at most log. Well, basically, if my ontology isn't too crazy, and DMOS actually is crazy, but if it wasn't too crazy, I'd need something like that many bits. So I basically now have a vector that is sparse, namely it's k-sparse with sparsity ratio log y over y. Okay, so that's good news. And then now I take this vector and project it to a lower dimensional space by compressed sensing. So I get some py out of it. Now we know from compressed sensing that I can reconstruct y from py for a random design y, even under some noise, provided that the noise isn't too bad, and furthermore, provided that my projection matrix P is well behaved. Okay. And basically, ask your friendly theorist for the latest conditions on what you need to do in terms of P and what noise you can allow for, and basically what those numbers are. Or you can also ask Yu Xiang. He's written a number of nice papers on that. Okay, and so then this is in a much lower dimensional space. So this is going to be close to log y. Okay, it's a little bit, it would be something like log squared y that you'd kind of need to do something meaningful. This is really back of the envelope type of reasoning. But then you basically infer some function f of x by regression, which tries to estimate, which basically just minimizes this. Just a squared norm. And as long as I can approximate this really well, I'll get some estimate here for f of x, and then I just run my decoder to get py, the solution from py, and I'm done. Okay. So here's a fun project that you could do. So effectively, the only reason why we picked this dictionary P is because, well, we ran a random number generator and we got some matrix and that's it. Now, there's a good reason why you might, it might turn out that some classes are harder to separate than others, right? It may be that you just got unlucky and didn't quite get an amazingly good dictionary. So you can afterwards optimize not just over F, but you can also optimize over P to some extent under a suitable reconstruction guarantee. And if you do that, then you probably get a slightly improved dictionary, and you'll get slightly improved error. The interesting thing would be to see how much you could gain there. Okay. So this is something you could do, and it will probably not be the world's most horrible optimization problem. Because you then need to solve the decoding step, so you want to make sure that your decoding is still accurate. You could, for instance, do that in a max margin Markov setting. Okay, good. So this is, yeah, kind of among the, well, crazy things you could do with compressed sensing in this context. Any more questions?
So would that detection of the P, would that be a separate problem that would not be a part of the picture?
Sorry?
P is not PSD or anything, so it's not really the problem, is not really the context.
Okay, so P itself here would still be all well behaved, right? So the problem is more that I also need to have my decoding condition. So you want to minimize this, and you can basically optimize F, or you can make the problem easier. But if you do this, then maybe you lose in the decoding, such that arg min over y bar of basically, P y bar minus f of x, such that this thing here minus y is small. Because right now inside here you are running a decoder. And I'm being very sloppy with the types of norms here, and you typically want to have an L1 norm somewhere and so on. So there's a lot more details here, but basically you can make the problem easier for you in aspects where the problem is easy to separate. And this is where you could possibly gain relative to the, in general, tight reconstruction with compressed sensing results. Because you're not dealing with arbitrary codes, you're dealing with very specific problems, and your classifiers may be able to solve some parts better than others. So basically your noise is not incoherent and it's not white. So this is basically why you should be able to improve in practice on the worst case guarantees that you can get from this. Okay. So I should probably move on here unless somebody has another question about this. But yeah, that would be a really fun thing to look at. Okay. So I want to get at least started with heavy hitters. And here's the challenge. So you get a data stream, and your goal is to find the k heaviest items for an arbitrary sequence. And then preferably, if I have a power law distribution, I want to get better guarantees. And by the way, if I want to find the k heaviest items, I want to do that in order k space, in order 1 over k accuracy. Or error, yeah. So why do you care about this? For instance, if you're trying to detect click fraud, right? Maybe there are some ads which, receive an unnaturally large number of clicks. You want to pick this up fairly quickly. Or maybe some users click a lot. Or maybe if you're Comcast or Time Warner and you want to screw people out of even more money, you want to find the users who use your service a lot. So obviously cannot really log all, what they're doing, but you want to be able to find out very quickly who your most active customers are, and then, maybe get rid of them or overcharge them such that, your balance sheet is good. Okay, sorry, I really like them. Or you want to find, popular keywords, trending terms very quickly, popular queries, network security. So, for instance, if somebody is launching a denial of service attack, you want to be able to detect very quickly, oops, okay, this specific IP address is receiving a lot of traffic. Just turns out right now that apparently you can use NTP for bandwidth amplification by basically having NTP respond back to somebody else with a long list of answers. So basically you get like a factor of 200 bandwidth amplification quite easily. So this is exactly where you want to be able to detect very quickly, oops, something bad is going on, and you want to find the heaviest terms. Okay. Now here's the challenge. Well, if I can log the entire traffic, it's fine. But even then, I still need to process it. And the other thing is that, an adversary might just order the traffic in, an adversarial way, such that either, all the important things happen up to some threshold in the beginning, and then I don't see anything of it again, and then it comes back in the end, for instance. That would be really evil. Or I only show you the stuff at the very end, or only at the very beginning. And the problem is you don't know beforehand what's going to happen, right? So it's actually very surprising that it's possible to design algorithms which do this thing. So when I first saw it, I was like, wow, this is really cool. So here's a simple algorithm. Okay. So it's called space saving, and this is by Manku and Motwani. No, sorry, it's by Metavali and forgot the other one. Manku Motwani is the lossy counting algorithm. Okay. So you basically initialize k pairs just like you would in a table of most frequent elements. And they consist of a counter and a label. And initially I set the label to be empty and the counter to be 0. And now I do the following thing. Okay, so I observe an element. If the element is in the set of pairs, I increment its counter by 1. If it's not in the set of pairs, I locate the label with the lowest count and update its count by 1 and rename the label. Okay. And everything's kind of super intuitive until you get to this point where you say, well, I'm going to reuse the old counter and increment it by 1. Why on earth would this work? Okay. So let's first look at what happens here. So let's say this is my initial table. So D's occurs with 2, C's, B's, and A's with 4. Then I observe an E. And without loss of generality, okay, I evict this guy here, the D. And since I evicted the D, well, I rename it to E and increment its count by 1. So I get E and 3. Okay, so this guy is clearly the last one. So then a B comes along, and I incremented the B counter, and then an F comes along, and I evict the C's and get an F and 3. Okay. It's like a crazy algorithm, right? Why would that work? Okay.
Because if you reject a single unique element,
Yes.
you don't like destroy the count of the remaining element.
Yes, and that is useful. It's useful because basically, if an element is evicted and comes back, you don't want its counter to be less than what you had before. Okay, so this is basically what we have, right? So if X is in the label set, increment the counter, else locate the label with the lowest count and, increment. Now, if you ever want to implement this, this is really just like a dozen line of code. Because, well, boost, so I guess everybody knows boost, right? Not boosting, but boost.org, the C++ library. If you do not, this is what you want to do right after class. Go to boost.org and look at this. A lot of the algorithms that you ever might want to have exist there, like lists, arrays, whatever. It's really useful. It's like the STL on steroids. Okay? And yeah, comes with most Linux distributions and comes with Mac ports, and I don't know, Windows maybe has it too. Anyway. So there's something called a bimap. And the bimap does exactly what you need there. It's a map, so it's mapping between keys and counters, so it's good, which is also ordered. And you can order it basically by the values, which is what we need, because we need to order it by the counters. So it basically maintains exactly the data structure that you need. You might almost think that somebody implemented this just to implement space saving. Okay, so basically don't do it yourself, just do that. So you can just quickly give me the smallest element, I'm done. Okay. Now, the obvious question is, does this algorithm do anything not totally crazy? Okay. So the first thing to think about is, well, at each step, one of the counters is being incremented, right? So if I observe n elements, well, so if I observe n elements, then in the end, the sum of the counters is n. Equals 1 to k. This is n. So from that it follows that the minimum counter is less equal than n over k. Right. Well, that just holds because, well, if I have n total and I have k bins, then the smallest bin cannot be larger than the average, though. Yeah. So now the next thing to notice is that if I observe an element, then the first time I insert it, well, the counter that it gets is greater or equal than 1. And then I keep on incrementing it. If at some point it gets evicted and then comes back, its counter can only have increased. Right? So therefore, I know that the value that I get for the elements in my data structure is always an upper bound on the number of counts that I have, that I truly had. Okay. Now, furthermore, I know that the largest entry in the counters is, n over k. So therefore, the largest error I could ever make by not seeing an element until the very end and then just keeping on inserting it would be n over k. So in other words, we get guarantee number 1, namely that the error is bounded by n over k, and the counter that I have in the data structure is always strictly an upper bound on the number of times I've seen the element. So it's basically nicely sandwiched. Actually, it turns out the bound is even tighter, and you can immediately read it off. You just look at the smallest entry in your data structure, and that is truly your upper bound. That's it. Okay. Now, guarantees 3, 4, and 3 to 6, I'm going to prove on Wednesday, because there's not enough time. But basically, what turns out to be the case is that if I have a distribution where I have a few very heavy elements and then the rest is really small, then this thing is even better. Because it very quickly locks onto the frequent elements and doesn't let go of them anymore. So that's why this is also sometimes called a heavy tolerant sketch. And there's an entire family of sketches which are called heavy tolerant. And then you can show that this thing is optimal, and you basically can show that by a simple construction. And furthermore, what we can also get is things like, well, basically the estimated position I majorized the true count at that position. So if I knew what the rank was, I could immediately look things up. So I'm going to go through all of those things in detail on Wednesday, and then we'll move on to other sketches and so on. But this was just to show you that there's a very simple data structure. So if you want, you can think about a little bit why those properties hold. And there's a nice paper by Radu Berinde, and I'm probably butchering his name. So Ina would probably know how to pronounce it properly. And so he's written a number of cool papers on that subject. Okay, good. So I'll see you again on Wednesday. Next week, Suvrit and I are not going to be around for one lecture, so we'll have a guest lecture on essentially prox operators and projections. So this is going to be a really cool lecture. Please attend. And then basically next week Suvrit will take over again in terms of optimization.